The universe is breaking, and we have the photographs to prove it. Out at a point in space, almost 1,000,000 miles from Earth, a 7-ton golden eye is staring back through time. It has been doing this since the summer of 2022, and almost every month since then, it has sent back an image that makes a room full of cosmologists go quiet. Not because the images are beautiful, most of them are, but because the images are wrong. Not technically wrong, not blurry, not corrupted, not the result of some software error. Wrong in the way that means our entire understanding of how the universe works might need to be torn up and started again. This is the James Webb Space Telescope, and the raw data it is sending home, the unprocessed images straight off its instruments before any human gets a chance to interpret them, is showing us things we were told for 40 years could not exist. The thing you need to understand about James Webb is that it is not just a better Hubble. It is a different machine, pointed at a different universe. Hubble looks at visible light, the same kind of light your eyes can see. James Webb looks at infrared, heat. And the reason that matters comes down to a single fact about how the universe expands. When light travels across billions of years of empty space, the space itself stretches. The light stretches with it. A flash of visible light from a galaxy 10 billion years ago, blue and bright at the moment it left its source, arrives at our solar system today as something far redder, far stretched, and in many cases shifted entirely out of the visible range and into the infrared. To put that in plain English, the oldest, most distant galaxies in the universe don't show up in visible light at all. They show up as heat. And until 2022, we had no telescope big enough or cold enough to see them properly. That changed when Webb opened its eyes. And within months of doing so, it found something nobody was prepared for. The first deep field image, released in July 2022, was meant to be a celebration, a demonstration of what the telescope could do. The team pointed it at a region of sky no bigger than a grain of sand held at arm's length, and stared at that one tiny patch for 12.5 hours. The image that came back showed thousands of galaxies, including some so far away that their light had been traveling for over 13 billion years. That was the headline. That was the press conference. That was the picture you saw on the news. What was not the headline was what some of those distant galaxies looked like. Because among the smudges and pinpricks in that field, scattered across a patch of sky smaller than a postage stamp held against the night, there were objects that simply should not have been there. Massive galaxies, mature galaxies, galaxies as large as our own Milky Way, sitting at distances that meant they existed when the universe was less than 700 million years old. By every model we had built over the previous half-century, galaxies that big should have needed at least 2 billion years to assemble themselves. Picture this. The universe is now about 13.8 billion years old. If you compress that whole history into a single calendar year, with the Big Bang on January 1st, and right now being midnight on December 31st, then the galaxies Webb was finding had to have formed inside the first 2 weeks of January. From nothing. That should not be possible. One of the first papers on these objects appeared in February of 2023. 6 galaxies, all caught in Webb's data, all far too massive for their age. The lead author, Ivo Labbé, from Australia's Swinburne University of Technology, told reporters his team was, in his words, mind blown. They thought at first that the results couldn't be real. The objects looked so bright and so big that some team members assumed they had made a mistake. It was Labbé's co-author, Joel Leisure at Penn State, who put a name on what they had found. He said the discovery created problems for science, that it called the whole picture of early galaxy formation into question. He started informally calling them universe breakers, and the name stuck.
What followed was a slow drip of confirmations. More deep field surveys, more analysis, more objects added to the list. By 2024, the catalogue of suspiciously mature galaxies in the early universe was no longer a handful. It was in the hundreds. Some of them appeared to contain old red stars, the kind of stars our own galaxy needed billions of years to grow. Others showed evidence of heavy elements, the kind only forged in the cores of stars that have lived, exploded, and seeded their material into the next generation. None of that should be present that early. Now keep that phrase in mind, universe breaker, because when we get to what Webb has found since, the universe breaker galaxies are going to look almost calm by comparison. About a year after that first paper, in mid-2023, a separate group going through Webb's deep field data noticed something stranger. Among the thousands of objects scattered across the images, there was a small population of compact red sources, tiny, sometimes barely resolved, and unnaturally red even for objects at the edge of the visible universe. They were given a deliberately bland name, little red dots, the kind of label scientists use when they don't yet know what they're looking at and don't want to commit to a guess. But the data behind those dots was anything but bland. Spectral analysis suggested that each one contained a black hole, and not a small one. Some of these objects appear to host black holes with masses in the hundreds of thousands, in some cases tens of millions of times that of our Sun, sitting at distances that put them in the universe's first 800 million years. And the dots are only part of a larger pattern. Across Webb's deep field images, in dozens of separate observations, researchers have been finding supermassive black holes that look fully grown. Some of the most distant quasars Webb has imaged contain black holes pushing 1 billion solar masses, sitting in galaxies less than 1 billion years old. To understand why that's a problem, take the Sun, that ball of plasma you cannot look at directly without going blind. Now take 1 billion of them. Crush every one of them together into a single object. That is what some of the largest of these early black holes appear to weigh. And the universe was less than 1 billion years old when they formed. There is no agreed-upon mechanism for how a black hole can get that big that fast. Black holes grow by feeding, by swallowing gas and stars and merging with other black holes. Even at the maximum theoretical feeding rate, what physicists call the Eddington limit, the math doesn't work. You cannot start with a stellar collapse, the death of a single massive star, and reach 1 billion solar masses in the time available. The numbers don't get there. They don't even come close. So what are these things, and how did they form? Nobody has a clean answer. Some researchers think the early universe may have allowed something called direct collapse, where a giant cloud of primordial gas crumpled directly into a black hole of 100,000 solar masses or more, skipping the star phase entirely. That would give later growth a head start. Others have proposed something stranger, hypothetical bodies called dark stars, theoretical objects powered not by nuclear fusion the way our Sun is powered, but by dark matter annihilation in their cores. If they ever existed,
They would have lived briefly in the early universe as enormous, cool, infrared bright objects. And starting in 2024, working researchers looking at Webb data began arguing in print that the simplest explanation for some of those compact red sources might be exactly that. There are scientists right now at universities from Texas to Colgate to the Space Telescope Science Institute looking at the raw images from Webb and proposing in peer-reviewed journals that the best candidate explanation for what they see is a class of object that, 12 months earlier, was considered pure speculation. If that were the only crisis Webb had caused, it would already be the biggest story in astronomy in a generation. It isn't. In October of 2023, the European Space Agency held a press conference. A separate team had been using Webb to image the Orion Nebula. The Orion Nebula is one of the most familiar objects in the night sky. About 1,300 light-years away, a stellar nursery where new stars are being born right now out of gas and dust, and have been for millions of years. Webb's resolution let them see the nebula in a way nobody had seen it before. And scattered through that nebula, drifting between the young stars, they reported finding something nobody had predicted. Pairs of objects, rogue, not orbiting any star. Each of them roughly the mass of Jupiter, or sometimes a few times more. Two of them at a time, gravitationally bound, slowly orbiting each other in the dark, while the rest of the nebula formed proper stars and planets around them. They named these objects jumbos, Jupiter Mass Binary Objects. And when the team finished going through the data, the count came back at over 40 pairs. 80 individual objects in a single nebula. There is no theory of star formation that produces these. None. Stars form when a cloud of gas collapses under its own gravity, and the smallest stable mass for that process is about 80 times the mass of Jupiter. Below that, the cloud just can't pack itself tightly enough to ignite the fusion that makes a star a star. Below that, you get a failed star, or a brown dwarf, or eventually a planet. Jumbos would be about 10 times too light to be stars. Stars that small shouldn't exist. They shouldn't form. They shouldn't be paired with other objects of the same impossible class. And they certainly shouldn't be drifting through space in 80-member groups inside the nebula they were born in. The European Space Agency, in announcing the discovery, used a specific phrase. They said it suggests that, in their words, there is some kind of process that we have not yet found. That is a polite way of saying we have no idea how these things got there. There is, in fairness, a wrinkle in the jumbo story now. In 2025, an astronomer at Penn State named Kevin Luhman went back through the original data with a sharper spectroscopic instrument. The 7 jumbo candidates he could analyze in detail turned out to be background sources, distant galaxies sitting behind the nebula, not planetary mass binaries inside it. The discovery hasn't been retracted, but the count is shrinking, and whether any jumbos truly exist is now an open question. Imagine what it would mean if even a handful of them are real. You are leaning back in a chair right now. The chair is holding you up against Earth's gravity. You weigh whatever you weigh because of where you are in Earth's gravitational well. Now imagine being a Jupiter mass object paired with another Jupiter mass object orbiting that partner in absolute darkness. No sun, no warmth, just slow circles in the cold for the next billion years. That is what a handful of objects in the Orion Nebula may be doing right now, and our best theories cannot tell us why. And there's a detail in the data that makes the surviving candidates stranger still. Some of the jumbo pairs are separated by hundreds of times the distance from Earth to our own Sun. They are bound to each other, but barely. A passing star, even a distant one, could pull one of them away with very little effort. We are looking at objects whose existence is itself fragile, drifting through one of the most well-studied nebulas in the sky, that we somehow missed entirely until Webb's images came down in the fall of 2023. So let's pull back for a moment. Let's look at what these three discoveries actually mean when you put them next to each other. Webb has shown us early galaxies that are too massive, too mature, too soon. It has shown us black holes that are too big, too fast, too early. And if the data holds up, it has shown us rogue, bound, brown dwarf-sized objects drifting in nebulas where they should not be able to form. Every one of those findings is, on its own, a serious problem for modern cosmology. Together, they suggest something more uncomfortable. They suggest that the foundational picture of how the universe got from the Big Bang to right now might be incomplete in ways nobody saw coming. The standard model of cosmology, called lambda-CDM, is a beautifully successful theory. It predicts the temperature variations of the cosmic microwave background, the radiation left over from the Big Bang, down to 1 part in 100,000. It predicts the large-scale structure of galaxies and clusters with extraordinary precision. For decades, every test we threw at it, the model passed. But it makes specific predictions about how fast galaxies should grow. It makes specific predictions about how massive black holes can be at a given age of the universe. And those predictions are now in open tension with what Webb is seeing. Some cosmologists are now using the word crisis, out loud, in print. And that crisis isn't being caused by anything exotic. It is being caused by photographs, by raw data, by the simple act of pointing a very expensive piece of glass at a sky we thought we had figured out and writing down what it actually looks like. Now, science has a long history of running into apparent crises and resolving them through better data, better models, or both. There's an optimistic interpretation here, and we should take it seriously. The pessimistic interpretation is harder. It is that some part of the model is wrong at a deeper level. That our understanding of how matter behaved in the first few 100 million years after the Big Bang has a hole in it. That dark matter, dark energy, or the inflation event itself, the rapid expansion of space in the first fraction of a second after the Big Bang, may not be quite what we think they are. And the reason this matters, beyond the academic, is that the cosmological model isn't just an abstraction. It is the framework we use to understand everything: the age of the universe, the formation of our own solar system, the composition of the matter your body is made of, the eventual fate of all of reality. If part of that framework is broken, then the picture we have built of where we come from and where we're going may be off in ways we don't yet have words for. To put a number on how strange this is, consider this. Webb has now imaged candidate galaxies at distances corresponding to a universe that was only about 290 million years old. Light has been traveling toward us from those galaxies for over 13.5 billion years. In that light, we are seeing structures that appear to have already done most of their growing up. Old stars, heavy elements, organized shapes, the kind of features our own galaxy needed roughly 10 billion years to produce. Webb is finding them in less than 300 million. It is the cosmic equivalent of going to a maternity ward and finding adults walking around. Caleb Scharf, a cosmologist and astrobiologist who serves as senior scientist for astrobiology at NASA Ames Research Center, put it bluntly in an interview last year. He said, "We may be living through the early years of one of those rare moments in science when the whole field starts to shift." He compared it to what happened in physics in the early 20th century, when the experiments started telling us that Newtonian gravity wasn't the whole story. This isn't a wholesale rejection of what came before. It's a recognition that what came before was a stage that worked beautifully within its limits, and those limits suddenly are visible. If you could stand outside Webb right now, 1,000,000 miles from Earth, a few times farther out than the Moon, you would see almost nothing. Even the Sun would just look like a particularly bright star. The Earth and the Moon would be a single, dim pair of points behind you. The instrument itself, gold and silver and quietly thermal, would be wrapped in its sunshield like a 5-layered silver kite. Each layer is about as thick as a human hair, and together they separate the cold instruments from the warm side facing the Sun. The temperature on the back of those instruments hovers at around -370 degrees Fahrenheit. That is colder than anywhere on Earth has ever naturally gotten, by more than 240 degrees. Colder than the lowest temperature recorded at Vostok Station in Antarctica, by a margin so large it almost doesn't make sense to compare them. That is the environment our most expensive scientific instrument needs in order to do what it does. And the reason it needs that cold is because warmer instruments would glow in the same infrared light they're trying to detect. The cold is what makes the seeing possible. And what it has seen, so far, is that we don't understand the early universe nearly as well as we thought. There is something quietly terrifying about that, and it isn't the kind of terror we usually associate with space. Not distance, not scale, not an asteroid hurtling toward Earth or a black hole at the center of the galaxy. It is the terror of being wrong. The terror of looking up at a sky we have been studying for 40 centuries, of building telescopes and theories and equations and a single, elegant story of how everything got here, and then finding out that the story might not hold. We built Webb to confirm the picture we already had. Instead, it is rearranging it. The mission is funded through at least 2030, with hopes for much longer. The instrument is using less fuel than expected, which means its operational lifetime keeps getting extended. There are dozens of observation campaigns planned, deep field studies that will go even deeper, spectral surveys that will look harder at the chemistry of those impossible galaxies, follow-up observations of the little red dots to figure out, finally, what they actually are, more targeted spectroscopy of the jumbo candidates to determine which, if any, are really there. Each of those campaigns is going to produce more data. Each batch is going to land in front of cosmologists who are already trying to figure out what to do with the last one.
Maybe that is what science is supposed to do. Maybe every era discovers that the previous era's certainty was a little overstated. Maybe in 50 years, we will look back on this moment and see clearly what we are only feeling the edges of now. But standing here in the middle of it, watching new images come down from a 7-ton golden mirror in the dark, it is hard to escape the feeling that we are at the start of a story whose shape we don't yet recognize. That the universe is older, stranger, and more crowded with mysteries than we wanted it to be. That every time we build a better instrument, we discover that the previous picture was a sketch. The only honest response, the only response that does justice to the data, is to admit it. The cosmos we thought we had figured out is showing us, image by image, frame by frame, that it had been quietly hiding things from us all along. We have 1,000,000 miles of cold dark between us and the instrument that is showing us this. And every month, the data keeps coming. We are not going to like all of it. Thanks for watching. I'll see you in the next one.